Welcome to the pre-recording of the first half of lecture 14, scheduled for the end of the fifth week in our 8-week summer course on computer algorithms. Today we're going to close off our brief excursion into dynamic programming when at the time it was still had much broader interpretation as scheduling. So we will start with scheduling and derive a solution for the subset sum and the knapsack problem. In the second half of this lecture, in the um, second following up pre-recording, we will consider the shortest paths in graphs that may have negative weights and introduce the Bellman-Ford algorithm. Okay, so what do we consider? We have one resource, and that resource is available in a time interval, 0 and the big W. We have a number of requests for this resource, and every request has a weight. So we don't really care when the requests are scheduled, but they all have a duration, a weight, the time that the resource will need to finish that request. So we would like to schedule as many requests as possible, or actually not as many requests as possible, but we would make a subset of the requests so that the sum of the weights is as large as possible, given the constraint, of course, that that sum may not exceed our time bound, the big W. So this is a constraint optimization problem known as the subset problem. So you could think of, we are given on input a set of numbers and a bound, and we are asked to compute a selection of those numbers so that the sum is as high as possible, but not exceeding our bound. So this is the subset sum problem, which we will next consider. Okay, so this is in the chapter still on dynamic programming, but it's an optimization problem. So let's see if we can solve this with a greedy algorithm. Greedy algorithms are in every step making one optimal decision. So here is the obvious optimal decision of the objects that you have to consider, of the numbers that you are given. You select the one that has the highest weight. So we select the heaviest request first. That's our first greedy rule. Well, what happens if we do that? Well, let's consider this sequence of 3 requests where the first request requires as much time as the total bound divided by 2 plus 1. So we're going to select that one first, but the other 2 requests require only half as much time. So you can see that the best selection would have been to select requests 2 and 3, but our greedy rule selected the heaviest request first. So this is a rule that will obviously not give us the best choice, and that's not a good rule. Okay, instead of picking the heaviest request first, what if we pick the lightest request first? So we have again the same problem, but another input. So that rule, the lightest request first, would have worked on the previous. So let's try it on another input. So the lightest request here is 1, and then we select the second request, which has this bigger W divided by 2 as weight. But obviously the maximum weight is now W2 divided by 2 plus 1. But again, just similarly like in the previous input, we would have done a lot better if we selected the second and the third requests. So also this rule fails. Okay, a greedy simple rule that sorts the weights and then selects in order is not going to work. So we are going to apply dynamic programming. Dynamic programming must be considered when greedy algorithms do not apply. So if you want to apply dynamic programming, you have to find a way to subdivide the original problem into subproblems. And that number of subproblems has to be a polynomial number, cannot be exponential, so this is not the brute force. For it to work, there must be a lot of similarity between the subproblems. So there is a kind of a natural way to look, and the algorithms are typically formulated recursively. So because they are based on a recurrence relation. Now, however, if you do not implement this carefully, we've covered memoization in 2 lectures ago, then it may not lead to an efficient algorithm. Okay, we have seen weighted interval scheduling. So what is weighted interval scheduling? We have there also one resources, and we have a number of requests with starting time, finish times, and we have a value. So here in this case, essentially the value might be our weight, and we have sorted on finish time. So the algorithm was also a programming problem that we considered earlier, but here for the subset sum problem, we do want and we do need a better way to explore the problem space. So there is similarity. It's not a scheduling problem again, but the algorithms that we have covered for scheduling problems do actually not apply. So this is also the bottom line of this slide. Okay, let's simplify our problem a little bit. So this is a course that has its focus on discrete problem. So the weights, they will be positive integers, and also our threshold actually will be a positive natural number. So we have a number of weights given, and then we are going to consider subsets where k is less than n, so we have n requests. Here we consider the optimal value of considering the first k requests. And the bound that we will consider, the big W, since it is a natural number, it makes sense to consider all possible values, since there are now finitely many, between 0 and that big W. So the little w is actually a parameter. Okay, so why does this make sense? Well, obviously, if your big W is very big, you may have to consider many choices, but then also in many practical problems, you actually have a relatively small value of the big W. So it makes sense in the subset sum problem. Things are starting to get tight if you have only limited time. If you have the W is actually a time constraint. If you have lots of time, it doesn't really matter how much time you spend on all your tasks that you have to do. It's a lot harder if you have to um, if you have if you are stressed in time. Okay, so we have discretized our input data, and now we can start to develop our recurrence looking backwards again. So we have n waits, n requests. Now, either we pick the last request, which means that either, or actually the slide starts with, we do not consider the last request. That means that the last request will not be part of any optimal solution. And then we simply have that the optimal solution is the optimal solution of the first n minus 1 requests. So which means that we simply ignore that last request. Or alternatively, and this is also something that we must consider. So this is divide and conquer. Similarly, we have a, but we don't use that terminology. Perhaps I should not have mentioned it even. Or in the other case, if we consider the last request, the optimal value for n consists of the weight of that last request plus the optimal value of the first n minus 1 requests, but now your bound is diminished by this last weight. Now, obviously, the second case only applies, is only valid when actually the weight, if you subtract the weight bound, it should never become negative. In dynamic programming, it's very important that the search space kind of decreases rather rapidly, and the subproblems that you consider are all very much related. So there is a relationship between the optimal values of the subproblems and the problem you want to solve. Okay, we can formalize this. So we have discretized our problem. So we are working now with a parameter, little w, which ranges between 0 and the big W. We consider all the sub-requests, their optimum value subject to the little w bound, which will be a weight, but which will also be an index. Now, again, it resembles very much the brutal force. If you think of all subsets of a set of n elements, that's 2 to the power n. So if you look at this problem naively, then this solving this by brutal force takes an exponential time. But the lemma will give us recurrence. And here you see the two cases, either, and now it's formulated in general for any little w, the weight. In the previous slide, it was the big W, but we can consider this for any number of requests k. So either we do not consider the kth request, and we cannot consider it if the um, last request weighs too much, weighs more than the allowed bound. Okay, so this lemma reads a little bit like an if-else statement in an algorithm, and it actually is intended to be used like this as well. So the else statement states that if you are considering the kth request, then you have to consider that either there are the two cases here now again, either you do consider it, but then you have the weight of the kate request and your bound diminishes or you don't. So in some sense, this lemma is a more precise formulation of the dichotomy. So if you want a formal proof of this lemma, you go back to the previous slide, where we actually derived the fact that the first case is only applicable if, say, the last weight or the current weight that you consider is larger than the bound that you can use. Okay, we have our recurrence, and actually we have our algorithm then. So this is our third lecture on dynamic programming, so we can go a little bit faster. Note, however, that for correctness, it's always good to consider the original recursive relation, then apply memoization, and then derive the direct iterative algorithm. But since this is the third lecture on dynamic programming, we are confident in the formulation of our algorithm, our dynamic programming problem. Okay, so on input we have a number of requests. So we have the weights of all the requests and we have the bound, the big W. We will set up a table, an array of arrays. The rows are corresponding to the items. We have one extra row for the initialization. The columns are the weights, also ranging from 0 to our big W. So we initialize the first row to 0, the first column actually to 0, the first statement here. And then we also initialize the first row to 0. The zeroth row and the zeroth column. So this is the initialization. Then the algorithm proceeds row-wise, considering the items one after the other. And we execute the recurrence from the lemma. So you see the if-else statement is actually embedded here. And it is a row-oriented algorithm. If you are more concerned with a column-oriented data structure, then the question would be, can you flip the rows with the columns? Can you do that? That's a question to keep in mind. So what we here claim is that it returns the optimal value, but actually what it returns is the value of the array of arrays, the top right corner of this table, which we build up from the bottom row by row. Okay, let us look at an example, a numerical example. We have three weights, 2 to 3, and you see the sum is 7, so we cannot select all of them. So we initialize the table. Column 0 is 0, so the columns are indexed by the weights. The rows are indexed by the items. So we have three items, we have three rows and our bottom 0th row. Okay, so let's run the algorithm. So if the weight is 1, then actually we can't schedule anything. But as soon as the weight becomes 2, then we can actually schedule the first item. So that's how we fill in that table. When we look at the second item, we cannot schedule if the W bound is 3. But as we persistently compute now the rows, we will see that as soon as the weight is 4, we can schedule it. And then we compute the next uh, table. So as you see from this simple example, the optimal value, the largest value that you can get to this is actually 5. Now the question is now, and the 5 is obtained twice. The question in the exercise that follows is, if you now return this value, uh, the algorithm only returns that value. What if you have access to this entire table of the algorithm? Can you recover the optimal solution or the optimal solutions? So this example has the benefit also by showing that the answer to this question is not necessarily unique. Okay, oops, what just happened? So let me go back to the point where I want to present the first um, exercise. And I have already indicated that the optimal solution might not be strictly exist, but because there are many optimal solutions. So demonstrate how in this, if you have access to the entire output table, not just the number 5, how you can recover by actually going backwards in this table. You look at the decisions that were made that got you there. So, and this asks you to go back to the previous lecture where we were considering sequence alignment and where I was indicating how to track the path. How can you here from the 5 on the top right below recover the optimal solution? We have formulated algorithms 2 lectures ago that show that you can recover the optimal solution, and this algorithm will also run efficiently. So the question is, um, the algorithm that we considered obviously terminated, and you can see that the cost is quadratic, or n times the big W. What is the recovery of an optimal solution? Okay, let me analyze the algorithm now. So we have obviously that we are dealing with a table, and we run through all the elements in this table. So it is at least proportional to the size of that table. So here I'm simply stating that the value, the optimal value, is computed in time the number of items times the value of that bound. One can prove this theorem by induction on the number of requests, observing then that in proceeding to the next item, you actually compute one extra row in the table. And in doing the computation of the one extra row, you do a constant number of additions. So you always add a weight and you compare two numbers. So there are a constant number of comparisons, a constant number of additions. So you have, if you actually go one item up, you go from n minus 1 times the big W, and you add n times the W. The big W is the size of a row. Okay, um, if you have n items, so given the table, the optimal set can be computed in linear time. And this is actually the answer to the exercise. So we follow one path, and we you follow backwards. So you could say you could formulate this easily recursively, and in every step you do one addition and two comparisons. So following one path in the table is linear. All right, here is another exercise. What can you think of? What about the space of this table? Here you consider 6 requests, and the bound on the table, the bound on the big omega is 100. So you will have a big table, 100 columns, and 6 or 7 rows. And so the algorithms are very simple. So if you really are bored writing 100 or 700 numbers, you could have a program that computes this for you. What you will observe is that there are many zero elements in this table. And here actually you so the exercise asks you to think about how to store what they call a sparse matrix. So sparse matrices are also used to store graphs. And in the previous exercise, you had to think about this table as a graph. Um, the other thing that I want to indicate here, you may have felt very uncomfortable with the discretization of our problem. Well, you could think of the 6 requests here as 3.3, 1.1, 2.7, 3.2, 3.7, and 3.1, where we essentially computed um, rational approximation. So where the denominator was 100. So we had the opposite way. So this is a discrete problem, but turning this into uh, continuous problem with 3.3, 1.1, 2.7, you divide all the numbers by 10. So if you have real numbers, you could think about crude rational approximation. You consider 2 decimal places in your rational approximation and you discretize it. But then you still have the more precise you want to be, or the more accurate you want to be, the larger your matrix, the more rows you have. But you can work with this then um, by a sparse data structure. Okay, let me finish with a variation of the problem known as the knapsack problem. So here is the formulation of the knapsack problem. We have again a resource and a time constraint on that resource, or we think about this now more as a knapsack. So you want to go on a trip and you have to pack items, you have to pack your bag, but we have too much stuff. Now, of course, some people, if they just have a toothbrush and some clean underwear, they are good to go. But let's assume that you are not packing lights, so you have typically the problem that you have too much stuff that could be useful on your trip, and you have to make a selection. Now, every object will now have a value, so it has a weight. It will fill up your bag, but it also have a value. And in some sense, in the subset sum, we were only considering the weights. So this is still fine if the heaviest objects are most important, but that's often not the case. So sometimes the little things are very precious. So we want to maximize now the sum of the values subjects to the weight. So this is a constraint optimization problem, very similar to the subset sum problem, but known as the knapsack problem. Okay, we will modify our solution to the subset sum problem so that we can solve this. Here is now again the derivation of the recurrence. Either we consider the last requests or we don't. We have again the constraint that if the last request weighs too much, then we don't, there's only the first case that matters, then we don't consider it. Otherwise, the modification is here indicated in red. Instead of adding the weight, we add the value of the last request if we consider the last request. Okay, so this enforces a little bit the subset sum. So in red, I have indicated the modification to the recurrence relation. So we again, we have discretized our problem. So the weights that we consider will range from 0 to the big W bound. And we consider the subproblems, which are subsets of all the requests of n requests, so n weights, n values. Then with the if else, we prepare the statement in our algorithm. We have not proven the correctness in the algorithm, but this follows again from the correctness of the lemma, which then led to a recursive algorithm, which we memoized, and which then led to the direct iterative algorithm formulated here for the knapsack. Again, I indicated in red the modifications of the subset sum. On input, we have now n additional weights, one extra array. We are going to modify also here in our else case, we are adding the value of the Kate weight, the current weight, when we consider it. Okay, so we know how to do things now, so let's nevertheless look at a numerical example. We have now 4 weights, an upper bound of 5, and 4 different values. The algorithm runs row-wise, so we initialize the first column by zeros and the first row also by zeros. So in the algorithm, we proceed row-wise, but I was asking, can you actually also proceed column-wise? Or can you actually go even in a diagonal fashion? So that's something to consider. As long as you have the previous elements computed. So here you see, let me explain again the rule. So typically one should be looking at the statement of the algorithm. But you can see that if we consider weight 1, if that is the bound, then can we actually schedule something? It does not appear the case. So although I see now there might be a problem. So if the bound of the weight is 2, then the optimal value is 12, although I think here this should have been a 10. The 10 actually appears, oh, I'm sorry. So we consider, I missed this, so let me go backwards. So this is the initial step. So the algorithm proceeds row-wise, so from the top row, from the bottom row up. So I was looking at the weights, I was confused with my own question. So, and indeed, if we are looking at the first weight, and now I'm doing things wrong, so let me erase things. So here it is. So if we consider the first item, then the first item has weight 2. So if your bound is 1, then obviously you cannot schedule it. So that's the reasoning here. If your weight is 2 as the bound, then indeed you can schedule and you have value 12. So this is why we have 12 there. Okay, so if the bound is 1 now, if we are at the second item, then we read this algorithm this way. So we execute it from the bottom up. Now, if considering the second item weighs only 1, then we can add it in our knapsack and we have the value 10. Now, if we consider higher bounds, if we have the bound 3, then we can actually schedule both requests, or we can take both the first two objects and we get the value 22. We continue considering the first 3 items on our next to last row, and then we see that the optimal value is 32. And the follow-up exercise will be to compute the value of an optimal solution. And here you can see that the optimal value is 37. This example is small enough for you to eyeball it, but the next exercise asks to compute an optimal solution given on input this table. So here is the exercise. If we look at this example again, and now the algorithm returned the top right value in this table, but if you have the entire table, can you trace the path that recovers an optimal selection? And also formulate that algorithm. So here is the point of this exercise and the first exercise as well. So what you actually here need to do, you first need to make sure that you understand on the example how to recover the optimal solution, and then you have to formulate it in general. You have to reason backwards. So in some sense, it's kind of a little bit appropriate. We start from a recurrence, we memoize the inefficient recursive solution, get to the direct iterative version, but then we think again recursively when we want to recover the optimal solution. Okay, the analysis is very similar to the subset sum, so it's an extension of the problem. We have an efficient algorithm for the subset sum, so therefore we also now have an efficient algorithm for the knapsack problem. The exercise is in some sense already solved, the previous exercise, so you have to prove this consequence. And the bottom line of the slide actually gives the essence of the proof, as you are following in your recursion only one path, and each time you do only one sum, some indexing that typically doesn't count, and you do a couple of comparisons. So that's how this exercise is solved. Okay, so this concludes the first half of the lecture. I hope that this was not too confusing and that you are getting a better grasp on dynamic programming.